Ever pondered over the mysteries of theoretical computer science concepts? Today we are going to unravel some of them. Theoretical computer science, a branch of computer science, delves into the mathematical aspects of computing. It's a universe filled with abstract models, algorithms, and computational problems. However, mastering this field can be a bit daunting, especially when it comes to understanding automata theory and formal languages. Enter JFLAP, an educational tool that makes this journey a tad bit easier. JFLAP stands for Java Formal Languages and Automata Package. It's a software tool designed to help you explore and understand concepts in automata theory, formal languages, and related areas of theoretical computer science. With it, you can construct and simulate finite automata, pushdown automata, Turing machines, and more. It's like a sandbox for theoretical computer science ideas. So, ready to dive into the world of JFLAP and explore theoretical computer science like never before? First things first, you need to install JFLAP on your computer. The process is quite straightforward. Kick off by visiting JFLAP's official website. Here, you'll find the download link for the software. Click on it and the download will commence. Alternatively, you can download JFLAP from other trusted software distribution platforms. Bear in mind, it's always safer to stick to known sources to avoid any risks associated with downloading software online. Once the download is complete, locate the downloaded file on your computer. It's typically in the Downloads folder unless you specified a different location. Open the file to begin the installation process. You'll be guided through a series of prompts. Simply follow the instructions and before you know it, you'll have JFLAP installed on your computer. Remember, if you encounter any hiccups during this process, refer to the JFLAP documentation or seek advice from online forums. Now that you have successfully installed JFLAP, let's move on to creating a finite automaton. Creating a finite automaton in JFLAP is like painting on a blank canvas. Let's get started. Imagine the canvas as your playground where you can construct an intricate piece of art, your finite automaton. To add states, simply click on the State tool. It's like picking up a brush to paint dots on your canvas. Each dot represents a state, so place them wisely and label each one accordingly. Next, you'll need to connect these states, much like connecting the dots. This is where the transition tool comes into play. Click on the source state, then on the destination state, and specify the input symbol for the transition. It's like drawing lines between your dots, each line representing a transition. Now, every finite automaton needs a starting point, the initial state. It's like the first dot in a dot-to-dot puzzle. Right-click on a state and select Set Initial to mark it as your starting point. Similarly, you'll need to designate one or more accepting states. These are the states where your automaton can happily end its journey. Right-click on the relevant states and select Toggle Accept to mark them as accepting states. And there you have it, the skeleton of your finite automaton. But remember, a finite automaton is more than just states and transitions. It's a dynamic system that can process input strings and decide whether to accept or reject them. To see your finite automaton in action, click on Input and select Test String. Enter an input string in the dialog box that pops up and click OK. JFLAP will then take you on a guided tour of your automaton, showing you the path it takes as it processes the input string. You'll see whether it accepts or rejects the string, bringing your finite automaton to life. And voila, you have created your first finite automaton in JFLAP. This is just the beginning of a fascinating journey into the world of theoretical computer science. The canvas is still wide open, waiting for you to explore further and create more complex automata. The fun part begins now, simulating your finite automaton. Let's get into it. Firstly, we need to provide our automaton with some input to process. To do this, we'll go to the menu bar and select the input option. From the drop-down, choose Test String. A dialog box will appear, prompting us to enter an input string. This string should be composed of the symbols we used when creating our transitions. After entering the string, click OK. Now, the magic happens. JFLAP will begin processing the input string, state by state, symbol by symbol. As it moves through each transition, it shows the path the automaton is taking. This visual representation is incredibly useful for understanding how the finite automaton processes input and changes states. As the simulation proceeds, you'll notice that each state the automaton enters lights up. This is a visual cue to help you track the automaton's progression through the states. You can follow along symbol by symbol as it processes the input string. Once the automaton has processed the entire string, JFLAP will indicate whether the string has been accepted or rejected. If the automaton ends in an accepting state, the string is accepted. However, if the automaton ends in a non-accepting state, or if there's no valid transition for a given symbol, the string is rejected. This simulation feature is a powerful tool for understanding how finite automata work. It allows us to see the inner workings of the automaton and how it processes input to arrive at a final state. Remember, practice makes perfect. Try simulating different finite automata with different input strings. Experiment with different configurations and observe the results. This will help you build a solid understanding of how finite automata operate. With that, you have successfully simulated a finite automaton in JFLAP. Congratulations! Now you're ready to explore more complex automata and dive deeper into the fascinating world of theoretical computer science. So let's keep going. JFLAP is not just about finite automata. It has a lot more to offer. Indeed, the versatility of this tool is truly remarkable. Let's delve a bit deeper and discover some of these other features. In addition to finite automata, JFLAP allows you to construct and simulate other types of automata, such as pushdown automata and Turing machines. Pushdown automata are particularly useful for understanding context-free languages, while Turing machines provide a more general model of computation. But that's not all. JFLAP also supports the creation and simulation of regular expressions. If you're a programmer, you might be familiar with these. Regular expressions are a powerful tool for pattern matching in strings. With JFLAP, you can create a regular expression, convert it into an equivalent finite automaton, and then simulate that automaton. Quite neat, isn't it? And the features don't stop there. JFLAP also provides support for context-free grammars. This means you can design a context-free grammar, convert it into a pushdown automaton, and then simulate that automaton. This is particularly useful for understanding how parsing works in compilers. But wait, there's more. JFLAP also includes features for simulating Turing machines. If you're not familiar, Turing machines are theoretical devices that define the concept of computation. They play a crucial role in the theory of computation, and with JFLAP, you can create and simulate your very own Turing machines. In essence, JFLAP is a comprehensive tool that allows you to explore a wide range of concepts in theoretical computer science. It's interactive, it's engaging, and it's an excellent way to learn and understand these concepts. Whether you're a student, a researcher, or just someone with a keen interest in theoretical computer science, JFLAP has something for you. Intrigued by all that JFLAP has to offer? It's time to start exploring. Let's take a moment to summarize what we have learned today. We've ventured into the fascinating world of theoretical computer science, taking a closer look at JFLAP, a powerful tool designed to help us explore concepts in automata theory, formal languages, and related areas. Our journey began with the process of downloading and installing JFLAP, a straightforward task that opens the gateway to a world of learning. With the software installed, we took our first steps into creating a finite automaton. We learned how to initiate a new project by selecting Finite Automaton from the list of automata options. This unveiled a blank canvas, a playground of potential where we can construct our automaton. We discovered how to add states to our automaton, label them, and use the transition tool to create transitions between states. Then we moved on to specifying the initial and accepting states, an important step that marks the starting point of our automaton and the states where it accepts input. Following this, we delved into the simulation of the finite automaton. We input a test string and watched as JFLAP showed the path of the automaton processing the input string, highlighting whether the string was accepted or rejected. But the adventure doesn't stop there. We also highlighted the versatility of JFLAP. Beyond finite automata, it offers the ability to create a variety of other automata, design regular expressions and context-free grammars, and simulate Turing machines. Remember, this is just a basic demonstration. The beauty of JFLAP lies in its depth and breadth, offering a wealth of features that you can explore further. It's a playground for your curiosity and a stepping stone into the wider world of theoretical computer science. So, that's a brief demonstration of JFLAP. Now it's your turn to explore, experiment, and learn. The world of theoretical computer science awaits you.